Hello everyone, welcome to today's third WJ3 Science Seminar in Post Working Group. Today we have two speakers, that Lukasz from Leiden Observatory and Mikhail from ESO. And Lukasz will present JWST observational research on young planetal stellar disks. Then followed by Mikhail will show the preliminary findings from the ALMA large program H Pro. So today we will embark on a journey through the evolution of planet disk from class 0 to class 2 stages. So if you have any questions, please use the raise hand function on Zoom to ask. And Joy and Elena, please keep an eye on any messages in the chat channel for us. So Lukasz, please go ahead when you're ready.
All right, I think I should see my full screen now. Good afternoon. Thank you for the opportunity to present my research today. My name is Lukasz Tychoniec, and I'm a postdoctoral researcher at Leiden Observatory. And today I would like to talk to you about young disks and how we actually characterize them with infrared facilities such as James Webb Space Telescope and sub-millimeter facilities such as like ALMA. And most of the data I will show today comes from the JWST observations of young protostars, also known as JWST program, led by Evina van Dishoek from Leiden. And the key paper I would like to present will be actually the work of Martijn van Helder, who also did the bulk of data reduction. So I want to take this opportunity to thank them. And the whole effort is, of course, also contributions to the JWST team. But without any further, let's jump into this big question: when do planets actually start to form? And I think there's been a mounting evidence over the past decade that show that planets at least should start forming early. When does the process actually conclude? It's a matter of debate, of course, but it seems that it's beginning important to understand the early stages of star formation so that we can understand the early stages of planet formation as well. So we're slightly shifting the scope here to the early stage, to the first 500,000 years of the star formation process. And as you've heard, Miguel will talk a bit about the later stages of the disk evolution as well. So what is the actual evidence that we have for the early planet formation? One comes from the fact that since ALMA became available more than a decade ago, we received many surveys of dust continuum of the class 2 disks, and they subsequently revealed that most of the dust masses in those class 2 disks are way too low to form even a single Jupiter core. And it later also ALMA and VLA surveys made possible to study the younger disks and showed that there seems to be a time evolution of how massive are the disks with their age. And so what also became available are the more than 5,000 planets known with through Kepler, through other missions, that now we can start to characterizing the masses, the compositions of the exoplanetary systems. So one of the key comparisons we've been able to do in the recent years was that we've been able to directly compare the masses of young disks, as you can see in this distribution plot here, and we were being able to compare with them with the exoplanetary system masses, as you can see in the black bar here. And we can see that the class 0 and 1 disks appear more massive than the typical exoplanetary systems that we observe, at least the most massive ones. So it seems that if we look at the younger stages, we can definitely form those systems that we observe all around the galaxy. And this is a slightly different representation of the data that I just showed, which shows all the exoplanets that we know and their masses as a function of stellar mass as well. And we show that class 2s are typically below the range of the planets that we find, the range of the masses of planets that we find, while class 0 and class 1 lie confidently in this regime where the planets are actually are. So it seems that at the early phases of star formation, at the first 500,000 years, it seems that we have enough building blocks, those dust grains, that will start from pebbles, planetesimals, and planets themselves. So I would like to move from that to saying that to understand the origin of planetary composition, so how actually the final composition of planets, both their rocky content, their gas content, How is it determined will depend a lot on the composition of the disks in the early stages before any kind of evolution starts ongoing, and a sort of dust drift, dust segregation, and gas segregation as well will start to occur. We need to look at those young and pristine disks, and we need to look at them in the regions where the planet formation should occur, so in the very inner regions of the system. It's not an easy task to study those young disks, especially those inner regions, because protostars are complicated structures. There's a lot of going on. There's a massive envelope that's still falling onto the disk, and there are outflows and jets associated with the process. So it definitely complicates the picture. Nevertheless, in the recent years, there's been a major developments in how we understand those young disks. For example, large program eDisk, as you can see an example here, and which studied at very high resolution the young disks, and it shows surprisingly few structures, gaps and rings in those young systems, probably suggesting that maybe it is the planets that are forming there didn't yet have time to even shape those structures, although the optical depth and the puffiness of those, this definitely doesn't help with trying to understand how those disks look in the midplane. And we have also more larger surveys coming up of a couple of hundred disks actually within the campus survey of the nearby star forming regions. It's been tremendous in showing us the large variety of disks, and this paper in particular studies the radii, but I think also in showing how diverse the structures can be, especially at the older systems. But it also shows that the further we go with age, the more common the structures are. And that's definitely true for the class 2, where there's plenty of those disks with large structures. So there seems to be an evolution happening in terms of dust, not only dust masses, as I said before, but also in the dust structures. And another thing that ALMA has been able to contribute is the gas studies of those young disks, showing us the cold gas and how we can study the physics, for example, through the temperature, because some of the species are sensitive to different types of snow lines, so we can trace physics, but still it remains very selective to the cold gas. It's very hard to get information on the hot gas with ALMA. So there's a dire need to go to shorter wavelengths, which will trace the hotter gas, as you can see in this nice plot from Anna Miotello's PP7 review, where to go both into the inner disk and to the closer to the protostar and closer to the disk surface, we need to start understanding, looking at the infrared range, because sub-millimeter is mostly sensitive to those midplane conditions. And JWST MIRI with the wavelength range from 5 to 28 microns is essential to reveal those inner regions of the disk. So the studies of these young disks is one of the focus of our JWST program. As I said, JWST observations of young stars. We targeted 16 low mass, 5 high mass targets with full JWST coverage. There are also some coordinated collaborations with the NIRSPEC program and USA MIRI GTO team. And I will focus in this particular talk, of course, with MIRI, with the rich wavelength range of the IFU capabilities comes many different sciences you can study. You can study outflows, jets, accretion, and ICES as well. But the focus will be indeed the inner disk, the molecular emission coming from the hot inner regions of the protostar. So this is how the MIRI data looks like, the IFUs, which provide us with a spectra in each of the pixel. We can draw maps of emission. And you can already see, compared with ALMA on the left, that some molecules, such as C2H2, acetylene, appear quite compact, seems to be unresolved emission coming from the center hot region, but while other molecules also have an extended component, such as CO2, seems to be aligned also with the outflow cavity. And this is how the spectra looks like. It's basically an embarrassment of richness. There's everything going on here. There's a lot of bright H2 lines, as you can see highlighted. There's iron, again, coming from the shocks and jets. And on the other hand, you have a lot of absorption features on this continuum, many of them coming from silicates, from water, but you can also clearly see CO2 at 15 microns, for example. But let's look a bit at the bottom. This is also a very rich spectra that sometimes might be confused with a noise, but no, it's just such a big richness of lines that we see here, and a lot of them coming from molecules, which will be the focus of this talk. So we can see water, we can see SO2, CH4, even SiO detected in a molecular in mid-infrareds. And on top of the emission, we also see in some sources instead an absorption from molecules, probably depending a lot on the geometry and the thermal structure of the source. So this is an example of source with very rich absorption features. And actually, let me take you on a little tour across all those lines. We see many detections, basically a forest of H2O lines here. And we will soon move also to SO2, which is shown in absorption here, and many other lines, including NH3, which should appear just in a second, and its first detection toward the protostar in the mid-infrared. So there's definitely a lot to digest when it comes to this data. But of course, what we are interested in and what will give us the most information is the comparison of an entire sample. So using the LTE fits and the SLAP models to those spectra, we try to understand what is the actual excitation temperatures of those molecules and their abundances. So I'm going to take you step by step through different sorts of molecules. First of all, we have water, cold water, but also warm and revibrational, so the hottest component of water. And we see that in some of the cases, in most of the cases, the range of temperatures that we see between class 0 and 1, and also with the older class 2, seems quite similar. But let me just mention that the revibrational water that we see here, the hot component above 1000 K appears only in 3 class 1 sources. So it's not that many of the targets that show this very hot water component. There are other molecules that seem to be quite similar between class 0 and 2, although we already see that CO2 appears a bit colder. This might be also related to the fact that I've shown you before that there's significant extended component. So even if all the spectra we are analyzing here and discussing here are extracted on source, even with JWST resolution, there will be a component probably of the outflow that's still encapsulated into this innermost regions. And there are also molecules that seem to behave very differently between different stages. So again, in color, you see class 0 and 1, and in the gray area, you see class 2, and you see that C2H2, HCN, they do seem to behave differently, showing much colder component in the class 0s versus class 2s. And there are molecules that are not yet detected in the class 2 systems, but appear not in too many sources, to be honest, but in some cases we see SiO, we see SO2. So probably something also interesting is hiding there. And yeah, I want to draw your attention to the numbers that we have here. In many cases, in let's say 75% of our targets, we detect water, but only in a few targets we detect molecules such as C2H2 and HCN. So those statistics definitely vary in terms of their completeness, but we are trying to squeeze out as much of the information, as much interpretation as possible. And so, yeah, again, are those few targets that we see which show very similar hot component in class 0, 1, and 2, are those tracing the hot embedded disks? So this is an example of a spectra of this very hot water lines in the class 1 system. TMC1W is one of the binary components of a protostellar system, and it shows very rich hot water spectra, possibly indeed coming from those inner regions. So it seems that in some class 1s, not too many though, only in 3 targets, we see those components above 1000 Kelvin, we can actually see the inner hot disk. So again, there are other molecules that not always behave consistently between class 0, 1, and 2. And what could they be tracing? The answer to that might lie in actually the abundances. So we tried to compare the abundances that we detect in a gas phase with ices. So as I said, with MIRI, we can also detect the ice absorption spectra. And for some sources, such as this B1C, this is one of the prototypical hot core that we show very rich ALMA emission in the complex organic molecules. So there's a big richness of ice coming, and we see the abundances between ice and gas are very consistent. So this might suggest that the origin of these molecules are actually from this hot core origin where icy grains are evaporating, and we see those molecules coming up to the gas phase. This is also consistent with quite low temperatures of 100 to 100 K. And so not necessarily coming from the inner disk, but coming from the extended warm disk region where molecules are sublimating. And we have also other cases where the molecules in the gas do not really agree with those in the ice phase when it comes to abundances. And in this case, L1448 is also well-known jet and outflow source. So we are thinking, our hypothesis here is that the molecules that we see coming actually from the outflow shocks, where, for example, HCN can be efficiently excited. So to slowly come to the summary of the results that we are getting from those molecules at different stages, we see definitely transitions between class 0, 1, and 2. In class 2, we typically see a lot of water lines, and saturation of water is very rare in earlier stages. On the other hand, in class 0, as you can see very prominently here, we see CO2 emission, but this might not necessarily come from the inner disk, and rather from the outflow component or the warm extended envelope. So there is definitely a lot of different mechanisms that are happening with class 0, 1, and 2. And that does not seem that it's so easy, even if the quality of the MIRI data to actually detect the inner disk and to actually understand what is the composition of the inner disk in the embedded stage. To quickly summarize the results that we are getting with JWST MIRI, we see indeed molecular emission within 100 AU scales, but not necessarily coming from the warm disk. We see that water and carbon dioxide are commonly detected in protostellar systems, but the temperatures of the molecules that we find are typically lower than those found in the class 2 disk. Again, highlighting that we are probably tracing different physical structures. So the relative rarity of those warm temperature components makes us think why we actually don't see the inner disk so commonly in the class 0 and 1 stage compared to what is observed in class 2, where hot water is detected very regularly. And so one of the solutions to that could be that basically very young disks, as they are evolving, it will take some time for the large grains and for the grains in general to settle in the midplane. So perhaps those grains remaining in the upper layers of the disk are basically obscuring the inner disk from our side. And this is a very important conclusion for also analysis of the dust evolution from the early to late stages, how fast this dust settling can originate. And from that, we can take two different conclusions. One is that, again, very young disks are probably not very settled. They indeed have much higher scale heights, and the dust here is not settled yet. And another conclusion is that we should be looking for those disks that are slowly transiting to the class 2 stage, where we can start seeing the mid-infrared, because again, I think it's really important that we detect the inner disk and the embedded stage, and that we try to understand what is the composition of the gas before the actual disk evolution takes a significant stage. I think I'm going to be slowly heading to conclusions in order to have some time for discussion. There's one more thing that I'm particularly excited about regarding MIRI data, and it's that let's say that indeed inner disk is practically hidden from us in class 0, but I think there's another cool way to how we can actually probe those inner regions, and this is the protostellar jets. And this is because those jets are usually launched from the very innermost regions of the disk, possibly carrying information on the chemistry that is occurring there. And indeed, I'm going to skip a lot of slides, but basically we zoomed in on one particular very cool system, BHR71, which showed to us this is the ionized iron. But what's particularly interesting about this source is that it shows a lot of refractory emission in the gas phase. So this is probably a result of dust being lifted from the inner disk and destroyed in those shocks, basically presenting us with the composition of those dust grains. So we are gonna work on the analysis of those jets and outflows and shocks to try to understand the composition of the gas that's coming from the inner disk. And another cool feature in this source is that we are seeing a dust continuum emission. So basically thermal emission right in the jet, which means that not all of the dust that's being lifted from the inner disk is indeed destroyed in the shocks. So to summarize, I think ALMA and JWST together offer us not only the very complete view of the disks, but also of the outflows, because now with outflows, you can also study the molecular component as is seen with ALMA, but also with JWST, we have access to a whole suite of lines starting from molecular hydrogen and then coming to a lot of refractories. Some of them we didn't even expect, such as cobalt. So coming to the conclusion of my and summary of my talk, I think JWST mirror is essential to study warm gas in the inner disk, but not on all targets it can actually be detected. And then protostellar jets launched from the planet-forming zones carry away dust and refractories, informing us about composition and content of those grains. And ALMA and JWST together, and their synergy is essential for a complete picture of early planet formation. And with that, thank you for your attention.
Okay, thank you, Lukasz. Very nice talk. And yeah, very good time manager. And we will have about 8 minutes to discuss and questions. So any questions, you can use the raise hand function on Zoom to ask. Okay, Barbara, please go ahead.
Hello, can you hear me?
Yes.
Yes.
Hello, okay, thank you for the very, very nice talk. I have maybe a more naive question. In the beginning, you talk about the warm and cold water molecules that you detect. What is the difference between warm and cold water, and how can you separate these type of molecules? Like, how do you know one is like colder and one is like the warmer one?
Yes, thank you for the question. So in terms of temperatures, the cold water that we are seeing is on the order of 100 to 300 Kelvin, and the warmers above that, basically from 300 to, let's say, 800. And the result of why we came to the conclusion that we need two components comes from the LTE modeling, where we basically try to fit the water with a single component. And while the fitting with a single temperature component works very well for most of the molecules, for water, we really need separate temperature components to fit it. This has been also shown in some of the class 2 systems, where clearly there was a need to include another cold component, and was actually a very nice evidence of the inflow of the pebbles into the inner disk. So the same was basically the case for us, where indeed also the richness of water spectra makes it possible for very accurate fitting of those lines, and seeing the lines at different components. We just use two different temperatures and try to fit to find the best match, and the two components fits are definitely the closest to the optimal.
So you think because they will have like different temperatures, so different, they will also behave differently in the disk?
In that sense, yes. I mean, in case of class 2, I know that's they should be coming from different layers. And also indeed, when you think about the thermal structure of a disk, yes, that would mean that the cold water we are detecting comes from slightly extended radius compared to the hot water, which should be coming from the in. And that is also pointing us to say that the hottest water, the one above 1000 K, is actually coming from the very inner disk, because that's only the regions where you would reach such temperatures.
Okay, thank you very much.
Okay, Antonio, please go ahead.
Ciao, Lukasz.
Hey.
Wonderful talk. You mentioned something that I think it's very interesting for me. When we talk about class 1 and class 2, I mean, there must be an intermediate transition between the two, right? So when you have all this dichotomy in the behavior, I wonder, can we define a set of objects that are actually in between these two stages, and can we maybe look at the properties of this object? Where do we stand in finding this object? And think of digital, maybe one of this object that is really in between, or not. I don't know.
Yeah, I mean, that's a great point. And I think like people already try to define a flat class stage coming from the SED turnover, right? From the negative to positive spectral indices, and saying that this should be the transition stage. But of course, it's more complex than that, because that a lot of this depends on inclination. So I think we need to look at more properties instead of just the spectral energy distribution. We can look for the disk properties, and indeed, the emergence of structures seems to be one indicator that the disk is actually evolving to later stages, right? But then we also have, well, not necessarily maybe, but we also have some very early disks that show this. But it seems that at class 2 they became common, and they're very rare in class 0. So there must be a transition somewhere. So we need to look for more of those features. I would be thinking also about jets and outflows, of course, because I think there's a clear evolution of the properties of jets from very molecular ones that we see in the early stages and purely atomic in late stages. So I think in the combination of those different traces, we can probably identify those candidates. Yeah.
So what is HL tau for you?
HL tau.
Yeah.
Well, I still think it's closer to class 2 than class 1 to me, but yeah.
Okay.
Yeah, okay, Edward, please go ahead.
Hello. You mentioned in your talk that dust been lifted up with the outflows of jets. Do you have estimates on the dust size?
Not yet. We are working on this, but it seems that it should be relatively small still, because we don't detect any emission in the ALMA, for example. At least in the jet itself, we do detect some emission along the cavity walls of dust, but nothing in the jet. So it seems to putting some upper limit on the sizes that is definitely lower than. It's definitely not millimeter size grains that we are lifting, at least not in high mount. But we still need to do the SED modeling of those continuum features. It's becoming a bit tricky because we also are heavily contaminated by the PSF of the central source.
Okay, thank you.
Hoping to get that, yeah.
Okay, does any questions? We still have a few time for a quick question. Okay, Kathleen, please.
Hi, yeah, I'll take the opportunity to ask something. Can you show us that lovely jet and the iron emission that you had again? And the
Sure.
spectra that you had of the jet as well? Because you made a comment that you weren't expecting to see some of these lines. So what made you go and look for all of these metals and metal lines then if you weren't expecting to see them?
Well, I mean, thanks for the question. I think the main point is that we saw those bright lines and just didn't know what they were, right? And then in the database, and it showed cobalt, and we didn't quite believe it at first. But then I started looking like supernova remnant studies, and this is where they came up. So that was quite interesting to see. Yeah. But it's basically, you know, it's a very different strategy, observing strategy than ALMA, right? You don't necessarily pick a frequency range to just get all of it, basically from 5 to 20 microns, and then you try to understand what's occurring there. Yeah.
So when you said that you went to the databases, did you go to the atomic line databases then? So yeah, the mains database and places like that. Yeah. Yeah. Okay. Interesting. Thank you.
Thanks.
Okay, let's thank Lukasz again and welcome Claire.
Thank you.
Yeah, and Claire, please go ahead when you're ready.
Okay.
Okay, please wait. I need to stop this recording and restart this.